Steinhauer here. Welcome back. Talking about the Big Bang and the beginning of the universe. And we've seen how it was extremely hot and extremely dense, and hotter and denser the farther you go back in time towards the beginning, t equals 0. So hot and dense, in fact, that at times it represents and is similar to the interiors of stars. So not surprisingly, the energies are high enough and the densities are high enough that nuclear fusion can take place. And in fact, we see that happen. Hydrogen atoms, in fact, will fuse and form helium atoms in similar ways to how they do it in the center of the sun. Interestingly, it was as hot and dense as you want to make it. So you might ask yourselves, interestingly though, it's only helium that gets fused. Heavier elements really don't get synthesized in any measurable quantity. So you might ask yourselves why that is the case. Clearly, there's no problem with energy. The further you go back in time, the more energetic it gets. You might wonder why more heavy elements don't get synthesized at all. And the answer is because it sort of happens backwards as the way it does in stars. In stars, especially massive stars, you fuse hydrogen into helium at one temperature and density. Once you run out of hydrogen in the core and it's all helium, then you contract and get hotter, and then you burn carbon into heavier elements. And then once you run out of carbon, you contract and get hotter and denser, and then you burn carbon and successive elements continually getting hotter and denser and hotter and denser. And building up higher and higher mass atoms. In the early universe, it happens in exactly the opposite way. And so before you can burn hydrogen into anything else, hydrogen turns into helium. It's already too cool to burn helium into anything else. And so you're sort of stuck with helium. And so it sort of works in the opposite direction. But we can make specific predictions about how much hydrogen and how much helium would be will be created in the early universe. And this is, looking at the nuclear physics that's going on and the conditions that are around. The predictions from the models suggest that for every 14 protons that are created in the early universe, there should be about 2 neutrons. And virtually all of those neutrons end up getting caught up in helium nuclei. And so for these 14 protons, 2 of them will get bound up with these neutrons and create this one helium nucleus, and there's really nothing left for these other 12 to do. So the predictions of nucleosynthesis occurring in the early universe suggest that for every 12 hydrogen atoms in the universe, we should have created 1 helium nucleus in the early part of the universe. And so by number ratio, it's more than 90% hydrogen, less than 10% helium. If you do it by mass, though, since this helium is 4 times as massive as this hydrogen, it's about 75% by mass should be contained in this hydrogen, and about 25% should be contained in helium. This is a prediction of the Big Bang nucleosynthesis and the elements that should have been created in the early universe. And when you look at the universe, this is almost exactly what we see today. There are heavier elements out there that we know have been created since, but if you look at primordial gases, meaning gases that are from the early universe and have not been contaminated with subsequent generations of stars, this matches almost perfectly. And it even matches the sun fairly well. The sun has 1%, a few percent other more massive things that have been created since, but by and large, this is about what we see even in the sun today. It's even better than that. This is a complicated graph, but it's showing you not only are helium and hydrogen created in the Big Bang, but very small amounts of deuterium are created. Remember, deuterium is a hydrogen atom that has 1 proton and 1 neutron. It's hydrogen 2. Very small amounts of helium-3 are measured. Very small amounts of lithium-7 are expected to be created. Detailed models of the conditions of the early universe have different predictions of how much of these various elements should be made, depending on how much density there was in the early part of the universe. And this is a tunable parameter in those models. But it turns out there's a specific number density, about 4%, where all of these not only agree with each other, but agree with the observations of what we see for those particular things. We can measure the primordial amount of deuterium and helium-3 and lithium-7, and guess what? They all agree at the same amount of ordinary matter in the universe. And guess what? That's the same amount of ordinary matter that we observe in the universe. You might remember we had ordinary matter was about 4%. We know dark matter was about 27%. And we had dark energy being the remainder to close the universe shape-wise. Well, here's another independent measurement that says, hey, an ordinary matter can only take up about 4% of the early universe to explain the abundances of all of these elements that we see today. This is, by the way, is further evidence that it can't be normal matter that's making up the dark matter. It has to be some non-baryonic thing, something that doesn't contain protons and neutrons, something like a neutrino-like particle. And remember, we might call those WIMPs, the weakly interacting massive particles. So this is a major success for the Big Bang theory. We can predict not only the abundances of hydrogen and helium, but also deuterium and helium-3 and lithium-7. The Big Bang theory makes predictions for how much of those things should have been created in the universe. We go out and we observe those things in the universe, and we get the same numbers. So this is another major success for the Big Bang theory. So basically, the Big Bang theory rests on these three pillars. Let's write them down because they're important. There's the Hubble law, the fact that the universe is expanding certainly projects backwards towards a hot, dense Big Bang universe. There is the cosmic microwave background radiation, the CMBR, which again is the smoking gun for a hot, dense past. And finally, there's a primordial abundances of the elements. Does this mean that the Big Bang theory is absolutely correct? Not necessarily, but any theory that you want to bring along to replace the Big Bang theory has to satisfy all of these conditions as well, and has to have a Hubble law, has to have an expanding universe, has to predict the cosmic microwave background radiation, and also has to get right how the abundances of all of these elements were made. So some Big Bang-like theory is almost certainly, are there details that can be tweaked and parameters that can be tweaked? Yes. Do we think we have some completely different theory that can match all of these things? It isn't necessary until we have some piece of evidence that contradicts the theories of the Big Bang. This works just fine. There are, however, still some mysteries about the Big Bang theory that need explaining. One is, how can the cosmic microwave background radiation be so uniform in every direction? I haven't mentioned this, but this is the horizon problem. When we look at the cosmic microwave background in one direction and in the opposite direction, we get exactly the same temperature. In fact, it doesn't matter what direction we look in, we get exactly the same temperature for the cosmic microwave background radiation. And this is unusual because those regions on opposite sides of the universe can't have communicated with each other. In fact, even now they can't have communicated with each other. We're only being able to communicate with those regions now from our vantage point in the middle. When you have a gas, it needs to interact with itself in order to come to a uniform temperature. So how is it that that uniform temperature was achieved when those two places in the universe can't have talked to each other? The other mystery of the universe is why the density is so close to critical. This is actually more of a problem than you think. We know that the universe is almost exactly flat. Now that's fine. Lots of parameters may be tunable. This is particularly interesting because the expansion of the universe should be moving us away from flat and not towards flat. In other words, if we look at the flatness of the universe as a function of time, let's say this is the curvature, some omega total value, right? And let's say this is critical. This is our flat universe. That's omega equals 1. If we started off even fairly close to, but just below the critical line, as the universe evolves, we should be evolving away from it. And if our universe was just a little bit above critical, up here, a closed universe, as the universe evolved, it should be evolving away from it. The fact that we're still way out here at t equals 10 to the 17 seconds, and we're still really close to 1, says that the farther back you go in time, it had to be arbitrarily, and in fact, exactly 1, almost, at the very beginning, within many, many, many orders of magnitude. So why is this? Why should we live in a universe that is tuned to be exactly the critical value, even from the very beginning? The other question, why is the distribution of matter so uniform? Basically, why is it that we look on large scales and matter? Again, we have the clumps and voids in the universe, but if we look on larger scales, there doesn't seem to be any region of the universe that is more dense than any other on the largest of scales. So these were still mysteries, but we have a particular theory that can address all of them and actually explain all of them in a specific way. So let's talk about that last piece that we need to add to the Big Bang theory to explain these particular mysteries. And that is an epoch of a period of inflation early in the universe. What do we mean by inflation? Well, we know the universe has been expanding, but it's been expanding at a fairly constant rate. I mean, it's been changing a little bit, but not anything crazy. There is a possibility that the universe expanded exponentially in the very beginning of the universe, like at 10 to the minus 35 seconds or so, right? So here's the normal expansion history that's been fairly linear since. Here is the fairly normal expansion of the universe before that, but it's possible, and we think that this actually happened, that at 10 to the minus 35 seconds, the universe grows by a factor of something like 10 to the 50. And this is an extraordinarily large number, right? This is what exponential expansion means. You can get very large very fast, even on this crazy logarithmic scale over here. Here is the approximate size of the universe, of the observable universe, at t equals 10 to the minus 30 seconds or so, whenever this ends. And that was sort of 1 centimeter. And of course, today we're at 10 to the 30 centimeters or so, right? The observable universe is really big. And there are various theories about what causes it, from some false vacuum. Anyway, there are ways to make this universe expand exponentially for a time and then also turn off. You can explain this with physics. Anyway, this can help explain all of the problems that we just ran into, because for the first 10 to the negative 35 seconds or so, the universe was much, much, much smaller than it is today. So how does this help us? Well, here is another way to look at this expansion. Let's say we've got 2 pieces of the universe, A and B, and let's say these are the pieces of the universe that now we're seeing on opposite sides of our observable universe, right? These are the clouds that we're seeing that have the same temperature on either sides of the universe. Well, according to the inflationary theory, those 2 blobs, those 2 clouds of gas, A and B, were in fact in thermal contact for the first 10 to the minus 35 seconds or so, right? That's not very much time, but it is enough time to thermalize, especially at the energies that we're talking about at 10 to the minus 35 to 38 seconds, post-Big Bang, right? So you've got 10 to the minus 38 seconds for those 2 gas clouds to become thermalized, and then the inflationary epoch rips them apart and brings them to opposite side of the universe, and we're just now getting the information from those separated clouds much, much later, billions of years later. So that can explain why it is, that can explain the horizon problem. It can explain why we see the same temperatures on either sides of the universe. It also explains the flatness problem, because whatever the shape was at 10 to the minus 38 seconds, let's say here's our 2-dimensional ant on our 2-dimensional universe, whether it was a closed sphere or whether it was an open saddle shape, it doesn't matter. If you increase the size of that sphere or increase the size of that saddle by a factor of 10 to the 50, whatever shape it had is gone. It looks flat to that ant that's sitting on it, because you've made the sphere so big that you can't even tell the difference between the sphere and a flat sheet of paper, because it's so big. And so it's possible that we have a non-flat universe, but in the inflationary era just erased all traces of it. And so we have a virtually completely flat universe geometrically today. Okay, we'll come back in the last video and talk about progress that has been made on understanding cosmology and the universe in the past couple decades, and also talk about the ultimate fate of the universe. See you there.